Authentication have more standard meanings. Integrity means the receivers must be assured that the email has not been modified in transit. And authentication would allow receivers to verify the sender's identity. Our focus here is more on confidentiality, so I will not go into details of integrity authentication except to say that they are more or less done by using standard PKI techniques. So now a little more deeper, a few more examples of where do we need this confidentiality. Is there actually sensitive information out there that needs this technology and this support? So I started out by saying that this is important for maintaining the privacy of sensitive information. For example, you have security lists concerning infrastructure protection. So we have some system administrators at NCSA and elsewhere that often discuss vulnerabilities and system characteristics, and they wish to keep this information away from the hackers. Today, they actually use an offline key distribution mechanism where they exchange emails on the phone. So they exchange passwords on the phone and then use that to encrypt the emails. So we need to provide a better solution for them. Another example could be executives discussing corporate strategies, where the corporate strategies will concern sensitive information. In healthcare research and development, you can imagine a group of researchers discussing healthcare issues, and they will need to encrypt any information to enforce HIPAA laws. That is, if they want to use email to do the research, but email is a very interesting, a very commonly used infrastructure, and it would be great if it could be used for a lot more purposes than it is done today. When you add integrity and authentication to the mix, secure email lists become important in all groupware applications, such as document annotation and storage, distributed software development, and mobile teamwork. So let's see how we do security for two-party email exchange today using something like PGP. Here, Alice has Bob's encryption key in her keyring, and Bob has Alice's signature verification key. Alice composes the message plaintext M, signs the hash of the message with a signature key using something like RSA or DSA, then chooses a random symmetric encryption key K and encrypts both the message and the signature using algorithms such as AES or TripleDES. She would then encrypt the symmetric key K with Bob's public key using something like RSA or LGMAL, base64 encode the whole message and send it off to Bob. Bob would use his decryption key to decrypt the message, specifically decrypt the symmetric key K, then further decrypt this entire part of the message and verify the signature. Other approaches such as PEM and SMIME are actually aligned, have very similar approaches to solving the problem. They work, but they're not used as prominently because of certificate distribution and revocation issues. An approach proposed recently that minimizes the distribution problems is identity-based encryption, where Alice would be able to derive a public encryption key for Bob using his email address alone. But if you try to use any of these solutions and extend it to a list scenario, you face a couple of challenges. The way to do it while ensuring minimum overhead for the users would be for the sender to encrypt the email with the list server's public key, for the list server to decrypt it and then re-encrypt it for every valid list subscriber. We have two problems. First, the confidentiality requirement is not met because the list server now can read the email contents. And secondly, an adversary can now compromise the list server to get access to all the emails that the list server maintains. That is, there's a high trust liability. So what are some approaches to solve this problem? One, as I said, like it's done today, you could just exchange a symmetric key out of band. But it's difficult to provide secure key distribution. You could just use a PGP web of trust, where the senders maintain all the receivers' PGP public keys for encryption. Clearly, that is a high key management overhead for each user. Or you could use cryptographic hardware, where the emails would be decrypted and re-encrypted in a crypto lockbox, such that it's difficult for the adversary to compromise that. Unfortunately, these lockboxes are expensive, costing anywhere from $3,000 to $10,000, and they also have been broken in the past. Our approach to this problem is to use software-based re-encryption techniques at the list server to transform encrypted email between the senders and receivers without the list server requiring access to email plaintext. So here's an overview of our protocol. So we have our entities, the list moderator, the list server, and a bunch of users that wish to subscribe to the email. When the group is created, the list moderator establishes a key called KLM. This is our LGMAL keys in a publicly known parameters, and the list server establishes a corresponding list key. They both implicitly agree that the sum of these keys is the list key, though neither knows its value. When a user wishes to subscribe to the email, it sends a join request to the list moderator. The list moderator replies with some key material that allows the user to establish its decryption and encryption key pair. It then completes the subscription process by sending a message and some key material to the list server, who establishes a corresponding list key for the user. And the idea is that the sum of the user's private key and the corresponding private key is also KLK, the list key. Once the users have subscribed to the list, you can send the email. The users would simply send signed and encrypted email to the list server. The list server would do the transformation and then forward the emails to all list subscribers who can decrypt and verify the signatures. An assumption here is that the list moderator is an independent entity not controlled by the list server. And the reason for that is if you compromise both KLM and KLS, you get KLK, and that can allow the adversary to violate the confidentiality of the solution, of the system. Okay? So how does it look like, putting it back in the format in which we saw how PGP works? Here Alice wants to send a message to the list, so she sends it to the list server. This part is exactly identical to what's happened earlier. Now instead of encrypting the message with the receiver's public key, she encrypts with her own public key and sends it to the list server. For a given list subscriber Bob, the list server would simply transform this part of the message and send it out to Bob. The transformation process mentioned here down below is very similar to what we saw as an example Elgamal transformation. That is, the list server simply encrypts the message with Alice's proxy key and decrypts it with Bob's proxy key to give a result such that the outgoing message is encrypted with Bob's public key. So the overhead is about the same as a decryption and re-encryption, but you minimize the security liability in the list server. We have recently formally verified the security of the scheme using ProVerif, which is Bruno Blanchet's formal verification protocol. It's a fully automated protocol verification tool. And now we're doing a prototype design and development. So for the client side, we're designing a web-based subscribe function that's integrated with the GNU-PG tools to generate standard PGP keys. So once we do this, any email client that employs a PGP plugin can use these tools. Now this is very important because we cannot say, if you want to use our solution, use a new email client. People are not going to do that. So we have to make the effort to integrate with PGP. That's the most commonly used security tool out there. And then, of course, we'll work on integrating with SMIME as well. And I don't think that should be a big problem. Now, on the server side, we're developing some plugins for MajorDomo and Mailman, which are the two most commonly used list server software. So that was what we have done for the email list infrastructure. And the idea is to use proxy encryption to minimize the trust liability in the list server. So now I'll move on to the second messaging infrastructure that we used, namely publish subscribe. So this is a relatively new but very powerful messaging paradigm. The idea is that there is a publish subscribe infrastructure comprising a bunch of brokers and border brokers. There are publishers that register with border brokers and advertise and publish events, for example, stock quotes. The broker network does the matching and routing of these events and then delivers them to subscribers who have registered interest in those events with the border brokers. So the publishers and subscribers do not interact directly. Instead, they use this messaging infrastructure, the PubSub infrastructure, to do the event routing. This messaging paradigm has applications in many areas, from software updates to location-based services and so on. As I mentioned, one commonly used example in this context is stock quotes, where the publishers just publish a stock quotes and the infrastructure figures out which are the subscribers that will be interested in these events and routes it to those events.